All right, welcome for those that are not here. I'll be recording most of today's session. Again, our topic is mass, weight, and gravity. I would like your notes the next time I see you, so I would need them by the end of the week going into the weekend. And one thing again with the notes is sections 1 and 2, basically guided reading. You go through the information in the section and you fill it in. I do have a PowerPoint for section 3, so I'll post that. So if you did not do section 3, or you just want to double check to make sure you had the correct response, I'll post that for section 3. Section 3 really focuses on Newton's third law. Section 2 focuses on Newton's second law. Then you get an introduction to Newton in section 1. Before we get into the relationship of mass and weight along with gravity, I did want to address, we had a student who sent in some questions on the notes. So I'll go ahead and do that here. The greater the force, this is from page 1 of the notes, the greater the force, the greater the motion. And one thing that relates to is something that we call a direct and an indirect relationship. So I'm going to go ahead and demonstrate that here. If you did the notes and you were looking at Newton's second law, is that a correct statement? Yes. You looked at Newton's second law, and that's the one with the equation we're going to work with. Simply put, that means force equals mass times acceleration. That is Newton's second law. It is commonly rewritten, though, in terms of acceleration. So if you just rework this equation to isolate for acceleration, you have acceleration equals force divided by mass. What I'm referring to in what that first screen grab was is the greater the force, the greater the motion. So when you look at it in terms of this equation, you have a direct relationship between acceleration and force because they're equal. They're just right across the equal sign. So that means if you had a greater force, right, if your force were to go up here and you did the math on this, that acceleration would increase. That's what we're talking about, a direct relationship. An indirect relationship would be if you had an increased acceleration, that would mean that your mass would go down. And then you can reverse all of these scenarios too. So if your acceleration goes down, that means your force goes down. And what do you think happens to the mass? The mass would go up. So again, you even have questions on some of your college exams, like the SAT and the ACT, where they give you scenarios. And really, it's just if you think of the equation in terms of direct and indirect relationship, you don't even need to do the math. You just need to visualize the numbers in there and what happens to each of the variables. So again, that first question a student had really relates back to this. And you actually get into that in the notes, I believe, when you get to section maybe 2. It's in there somewhere. I saw it. So the second one, the second question is from the notes is what would the free body diagram look like for a crystal hanging from a string? One thing to note is we're not going to spend a lot of time on you sketching out. I mean, you should initially. I'm not gonna, it's more for you just to visualize the problem. So for that one there, again, one thing you need to do is this is actually, here's another way you can rework this problem, is A equals, and I believe it goes like this. It's a Greek letter that means the sum. So it's really the sum of all the forces. So some of these problems are asking you to think in terms of forces. So the particular question the student wanted to know is what would the free body diagram look like for a crystal hanging from a string? So again, you could just draw, this is a crude crystal, right? And it's hanging from a string, right? So what are the forces involved? Well, going in this direction is you're going to have the force of the string on the crystal. That is going in an up direction. And then you're also going to have the force um, of Earth's mass. So really you're just talking about the gravitational force. So those would be the only two forces on that. Again, we're not going to get too involved in all these different scenarios, but you do want to think about the forces. Let's say you had a box and you were treating that box like a tug of war. What would be the forces involved there? So this kind of incorporates all of them if you get there. Let's say it's me and Andrew on each side. That would be me. Here would be Andrew. What other forces do you know that are involved if we were each pushing on that box? What other forces are involved if it's sitting on the floor? There's two other forces that you maybe should have gleaned some information from the notes. Is there a force going down? Again, the force of gravity. So if you have a force going down, who remembers what that force is that opposes? It opposes gravity or opposes the object at a perpendicular angle. Ooh, come on! I'm recording this too. Did that sound creepy for those of you playing school at home? Any whoozle? That would be the normal force. So the normal force opposes objects, opposes the gravity going perpendicular to the object. So again, if you had me and Andrew pushing on a box, you were sketching it out, this all it does is really just visualizes. So really in this case, so clearly I would be the winner. Let's say I would be applying 50 newtons in one direction. Let's say that would be east. Andrew, because he's a weakling, is applying 35. Oh, I forgot. I'm recording this so people could use this as evidence against me. Oh, well. It was nice teaching you guys. Andrew's pushing with a force of 35 newtons, right? If you were looking at a problem, then really it's just the sum of all these forces. The normal force and the gravitational force are going to cancel out. Then it's just a matter of which direction, say east or west, the box is going. And just from the numbers, it really doesn't matter who's pushing it on or who's a weakling or not. It's just a matter of the numbers. And you can see in this scenario, you would wind up having a force of 15 newtons, in an east direction. So again, the free body diagrams are just really meant to help you visualize some of the problems. And then the third question that a student asked was the acceleration of an object is equal to the sum of the forces divided by the mass. Which wheelbarrow will move faster if pushed with the same amount of force? So, and why? So again, this goes back directly to that indirect conversation we just had. So really what you have is you have two wheelbarrows. And again, it had to refer to the notes earlier. I don't know how to draw a wheelbarrow. Right? And let's say you had, again, 50 newtons in there. You have 25. Or no, we're just going to go with mass. So let's say you've got 100 kilograms here, and you've got 75 kilograms here. And again, what they're saying is if the force is the same, let's go back to the question. The acceleration of the object is equal to the sum of the forces divided by the mass. So the wheelbarrow, which will move faster. So we really want to look at the greater, which acceleration is going to be larger. So force over mass. And again, if you're applying the same force, and let's say the mass here is greater on this one, then that acceleration has to go down. So really you're thinking in terms of that inverse relationship when you're comparing the two wheelbarrows. You would accelerate the one that's has a lighter mass more than the other. All right, so that takes care of that. Now we're going to focus on mass versus weight and gravity. So that's what we're going to be looking at today. So go ahead and open up a new page. And again, we're looking at mass versus weight. Right? So mass is again how we're determining the amount of matter in things in science, and we use it in kilograms. Weight, when we think of weight, somebody says, how much do you weigh? You give a number because you can step on a scale, you weigh 175 pounds, you weigh 110 pounds. Again, you can convert that into kilograms. You've got some conversion charts and you can convert that. But what is weight in terms of physics and science? It's different than how you view it as like 110 pounds. Weight is a force. So when you went through the notes, there's different types of forces. You've got, gravity is going to be a force, the normal force. You can have forces from tension. You can have, again, a force from weight. So remember our acceleration or our Newton's second law problem here, right? So we can also view this using this as our guide. So weight, again, is a force. It's going to equal the mass of an object. And instead of using the A, you're going to use G. So it is an acceleration, but you're using the acceleration as it relates to the local gravity. And I said local gravity because it depends on where you are. Another thing you should have learned through the notes is that what unit do we use for force? Newton, yeah. So your weight's going to be in Newton. What is going to be your unit for mass? Kilogram, not gram, kilogram. That's going to be your unit for mass. And I just said gravity is a type of what? Acceleration. So again, you're going to have your meters per second squared. These are the units for your weight, equation. When we get to some Newton's second law problems coming up on Tuesday and Wednesday, the problem might give you, you got to remember to make sure that you're in, it might give you the weight of an object and you need to convert it into mass or vice versa. Right, so I've got a couple problems here. What is the weight in pounds of a 7-kilogram bowling ball? So we were looking for the weight. This is not newtons, so weight in pounds of a 7-kilogram bowling ball on Earth's surface. So there's a couple of ways we can do this problem. This would be one of them. Right? So again, really this is just a conversion problem because we're looking for it in pounds, not as a force. So you have 7 kilograms, and then 1 kilogram is going to equal 2.2 pounds. So that's a conversion you would want to know. 1 kilogram equals 2.2 pounds. And if you do the math, it would be 15.4 pounds. So there it is. Let's see what else we can do here. Ooh. All right, let me go ahead and pause here for a second. Okay, so here's this next problem, next example is we're going to look at what is the weight as a force of a 78-pound weakling standing on the moon, right? So here's how we can attack that problem. So we've got a 78-pound individual. And again, we need to get that into kilograms, right? So we're going to use a conversion then. 1 kilogram is going to, I think it was, let me see here, it's going to be point. This. All right, so we're going to go from pounds to kilogram. So 1 pound is 0.45 kilograms, right? And then I can go ahead and I can get that into kilograms is what I'm going to need. So 78 times 0.45 equals 35.1 kilograms. So that was the first thing. I went from how we view pounds here in the US, a 78-pound weakling, and converted it into kilograms. And remember, ultimately, we're looking for weight as a force of a 78-pound weakling standing on the moon. All right, so weight force, now we've got our first thing, so we've got 35.1. Now, we know on Earth that our acceleration due to gravity is 9.8. That's a standard. You can always use 9.8. On the moon, since the moon has 1/6 of our gravity, simple calculation, if you did 9.8 divided by 6, you come up with 1.6. So on the moon, that person's weight as a force would be 35.1 times 1.6, which would be 56.16 newtons. And since the only number you were given originally was 78, which is 2 significant digits, you can just make that 56 newtons. So a 78-pound weakling on Earth has a weight force on the moon of 56 newtons. All right, so again, some of the conversions you can use is you've got 1 kilogram equals 2.2 pounds. 1 pound equals 0.45 kilograms. And then you're looking at your local gravity. So Earth is going to be 9.8 and the moon is 1.6. And again, because these are accelerations, meters per second squared, meters per second squared. And again, just like the 3,600 seconds in an hour, these are, just some things that, especially if you're playing along in physics this year that you kind of readily remember. This one definitely. Some sources you might see 9.81. I like to just stick with 9.8 and then think of it, the moon is 1/6 our gravity. So when you divide it through, you got 1.6 there. All right, thank you for listening. Any other questions, email me. I will post the assignment in just a minute, dealing with mass and weight, and then we'll move on to include this into our discussion with Newton's second law tomorrow.